Hello, dear listeners, and welcome to a new episode of our Letter to Vox podcast. Today's deep dive takes us right to the heart of how we establish and accept human knowledge, specifically how we define scientific progress itself. For centuries, the ultimate intellectual ideal was certainty.
Right.
Intellectual honesty meant you only dared to utter what was absolutely proven, established either by sheer logic or by the unchallengeable evidence of our senses.
But that ideal, well, history and philosophy showed it was a complete fantasy.
Exactly. We are diving into the dramatic collapse of that notion and the really sophisticated, ingenious system developed to replace it.
A system that argues that true progress isn't about proving theories true at all.
No, it's about systematically and rationally managing these bold, powerful, but inherently fallible ideas.
And to really appreciate the magnitude of this shift, you have to grasp the philosophical crisis that made it necessary.
It wasn't a sudden thing.
No, not at all. The collapse of certainty, it started with these fundamental challenges to where our knowledge even comes from. The major earthquake that really set this whole crisis in motion was delivered by David Hume back in the 18th century.
Hume is the philosopher who, if I'm remembering this correctly, basically challenged our right to assume the future will resemble the past.
Right. That's a perfect way to put it. Hume argued that when we observe the world, we see a billiard ball hit another, and the second one moves all experience shows us is that one event regularly follows another.
So we see a pattern, a constant conjunction, I think is the term.
Exactly, constant conjunction. But we never, ever observe the necessary connection. We don't see the causality that says the first event must cause the second.
Which means basic principles like causality. You can't get them from sense experience alone.
You can't. It's just a habit of the mind, a psychological expectation. It's not a certain rational necessity.
That is deeply unsettling. I mean, if you can't even logically justify the principle of cause and effect from observation, then the entire structure of science,
The whole thing, which relies on predicting future effects from present causes, is just resting on quicksand.
and that anxiety is precisely what triggered Immanuel Kant.
Ah, okay.
Kant took Hume's conclusions very, very seriously. He dedicated his entire project to securing a foundation for knowledge, specifically Newtonian physics and Euclidean geometry, that would be immune to this kind of skepticism.
So he was essentially trying to save science by saying some knowledge isn't derived from experience, but is built into the structure of the mind itself.
That's the core of his massive project, transcendental idealism. Kant tried to establish that certain principles, the very preconditions for us to have any experience at all, were known a priori.
Independently of experience.
Right. His hope was to secure these core scientific principles with absolute certainty to provide a stable, unchallengeable framework.
He was trying to prove that even if we can't prove things from the outside world, we can prove them from the inside, so to speak. That our own mental framework guarantees certain truths.
A brilliant attempt. But history delivered the ultimate punchline. It did. The very theory he was trying to secure with certainty Newtonian mechanics was eventually overthrown.
Right. When faced with things like high-velocity physics, relativity, and these tiny anomalies in planetary orbits, I mean, if the most robust, successful scientific theory in history, something held as certain truth for centuries, could be proven false.
Then the whole ideal of certain proven knowledge, what you philosophers call justificationism, had just fallen into ruins.
Completely. The foundational assumption of intellectual life since Plato, really, that rationality means seeking and stating only proven truth, was logically and historically demolished.
And that leaves you at the edge of an abyss, doesn't it?
It does. If all knowledge is fallible, unprovable, and temporary, how do you distinguish science from pseudoscience? How can you say one theory is better than another?
Which sets the stage for a new kind of rationality, one based entirely on ruthlessly eliminating error.
And systematically managing our inherently fallible theories.
Okay, let's unpack this and introduce the thinker who provided that rational structure. Our mission today is to dive deep into the work of Imre Lakatos, who transformed falsification from a simple test into a sophisticated historical process governed by what he called scientific research programs.
And this framework, it provides the objective, rational standard for measuring scientific growth in a world without any certainty.
Let's start with the architect himself, Imre Lakatos, a man whose life, it perfectly embodies this clash between arbitrary power and the search for objective truth.
Absolutely. He was born Imre Lipschitz in Debrecen, Hungary in 1922, and he died prematurely in London in 1974.
And his early life was just dominated by the political turmoil of mid-20th century Europe.
His biography is really a testament to the dangers of intellectual life in that era. To evade persecution by the Horthy regime and the anti-Jewish laws during World War II, he had to change his name.
Twice, right.
Yes. First to Imre Molnar and then later to Imre Lakatos. And this wasn't just a name change, it was a necessary survival tactic.
A way to continue his work. And he was highly intellectual, studying mathematics, physics, and philosophy. But his political life, which involved active participation in the Communist Party, eventually led to, well, serious consequences.
Indeed. After the war, his intellectual independence just clashed with the party line. He was imprisoned for revisionism, which was basically the charge they leveled against anyone who questioned orthodox Marxist doctrine.
And that experience of seeing a powerful ideology just reject logic and embrace dogma must have shaped his entire philosophical outlook.
Deeply. After the Hungarian uprising in 1956, he fled the country, and he eventually earned his second doctorate in philosophy at Cambridge.
So his personal fight against arbitrary political dogma fed directly into his intellectual fight against arbitrary scientific dogma.
Precisely. His real role in intellectual history was as a critical mediator. He arrived at a time when the philosophy of science was really split between two giants, Karl Popper and Thomas S. Kuhn,
Popper, the champion of falsificationism.
arguing that science progresses through the rapid, ruthless elimination of error. And then you had Kuhn, who introduced the concept of the paradigm in his hugely influential book, The Structure of Scientific Revolutions.
And Kuhn's work was often interpreted as highly relativistic, wasn't it?
Oh, absolutely. Kuhn stressed the sociological continuity of what he called normal science, where scientists kind of dogmatically stick to a framework until the anomalies just pile up so high that the whole thing shatters.
A scientific revolution.
A scientific revolution. But Kuhn often described the shift between these paradigms as non-rational. He compared it to a religious conversion rather than a logical progression.
Because the two sides are basically speaking different languages.
Exactly. They have different standards, different languages. And that sounds like intellectual anarchy. If scientific progress is just one group of stubborn scientists replacing another for sociological reasons, how can you claim science is rational?
That was the problem Lakatos set out to solve.
That was his entire mission. His primary aim was to show that scientific revolutions are not these arbitrary shifts dictated by psychology or mob rule,
but are instances of rational progress.
driven by objective criteria of growth. He wanted to find a methodology that preserved the tenacity and the continuity that Kuhn observed in real science, while insisting that progress remained logical, not arbitrary.
And we should also mention his intended collaboration with Paul Feyerabend.
Yes, his great friend and intellectual rival. They were going to write a joint work and debate between the rationalist, Lakatos, and the philosophical anarchist, Feyerabend,
Feyerabend's part became the famous book Against Method,
which argued that there is no universal scientific method and concluded famously that anything goes.
which is the ultimate challenge to rationality.
It is. And tragically, Lakatos' sudden death in 1974 cut short his chance to fully articulate his defense. But the methodology of research programs stands as his detailed attempt to provide that objective, flexible, yet critical methodology. So before we get into Lakatos' solution, we have to clearly define the landscape he inherited. Specifically, the failures of what he called dogmatic or naive falsificationism.
Okay, so this was the idea that came right after justificationism, after the dream of certainty died.
Right. It conceded that theories could not be logically proven. That was impossible. But it clung desperately to the mirror image, the idea that theories could be logically disproved with absolute certainty.
Using hard, firm facts.
Exactly. The rule of the game was simple. You state your theory, you define the experiment that would kill it.
And if that experiment shows a contradiction, you have to reject the theory unconditionally.
Precisely. The core rule was that a theory is only scientific if it is falsifiable. Intellectual honesty required specifying that fatal experiment in advance.
The theoretician has to yield to the experimentalist.
Yes. But this deceptively simple idea, this idea of a decisive no from nature, it just doesn't work.
And Lakatos delivered two devastating critiques against it. Let's start with the problem of pure observation.
Lakatos' first point is crucial. There are no pure, untheoretical observations. All observations are, to use his term, theory impregnated.
Theory impregnated. So when we look at the world, we don't just register raw data.
Never. We interpret it through a network of expectations, concepts, and instruments that themselves rely on theory.
Okay, give me a concrete example. If I look at the moon, I see the moon. Isn't that a hard fact?
Let's go back to Galileo in the early 17th century. He was challenging the Aristotelian cosmos.
The idea that celestial bodies were perfect, flawless spheres.
The hardcore belief, yes. And Galileo claimed to observe mountains and valleys on the moon using his telescope.
And to us today, that's an open and shut case. We know the moon has mountains.
But not to his contemporaries. Lakatos points out that Galileo's claim rested entirely on the optical theory of the telescope. And at the time, that theory was new, it was controversial, it was often unreliable.
So his opponents were actually justified in arguing that the mountains could just be optical illusions produced by the imperfect lenses.
They were perfectly justified. It wasn't a clean fight between an infallible fact, the mountains, and a weak theory. It was a clash between Galileo's interpretation, relying on a fallible, new optical theory,
And the Aristotelians' interpretation, relying on their established, accepted theory of the heavens.
Absolutely. The demarcation line that dogmatic falsificationism needs, that line between soft, unproven theories and a hard, proven empirical basis, it's a myth. All propositions in science are incurably fallible.
Wait, let me just stop you there. You used the phrase modus tollens earlier to describe how this is supposed to work logically. Can you break that down? How does the fact that facts are shaky break the logic?
That's a great question. Modus tollens is the rule of elimination. In logic, it says, if your theory, T, implies an observation O, and you find that observation O is false, then the theory T must be false.
Okay, that seems straightforward.
It is, but it depends entirely on having a rock-solid, non-theoretical, not O, a hard fact, to logically conclude not T. But if your not O is itself shaky, because it relies on a fallible observation theory,
Then the logic just breaks down. You can't definitively kill the theory.
you can't. You can always blame the instruments of the observer or the math that interprets the observation.
That's profound. But now let's move to the second critique, which deals with the theories themselves. The ceteris paribus clause.
This is the logical death blow. The most important successful theories, like Newton's theory of gravitation, are prima facie undisprovable because they implicitly contain a universal non-existence clause.
Ceteris paribus, all other things being equal.
Exactly. Let's use the famous anecdote of the imaginary Newtonian physicist. Imagine this scientist uses Newton's law, which we'll call N, to predict the path of a new planet. The observation, O, shows the planet deviates from the predicted path.
So if he were a dogmatic falsificationist, he would have to reject Newton's law. The prediction failed.
But historically and rationally, he does not. He proposes an auxiliary hypothesis, A1. Perhaps there's a hitherto unknown planet, Pn prime, that's perturbing the path.
So the blame is diverted away from the core theory and onto the initial conditions.
Right. And if astronomers then use a bigger telescope and they don't find this new planet, does he abandon Newton then?
I'm guessing not.
Not yet. He proposes A2. A cloud of cosmic dust is hiding the planet. Or maybe there's a magnetic field. Or maybe the telescope's mirror has an unknown aberration. The target for refutation remains frustratingly elusive.
The implication here is enormous. A theory like Newton's law only contradicts an observation on the condition that no other factor has any influence.
But that condition, the ceteris paribus clause, is itself a universal non-existence statement. And you can't prove a universal non-existence statement with a finite number of observations.
You can't observe and prove that no other factors exist.
Never. So the theory itself can always be saved by diverting the blame.
And that's the core irony. The attempt to use firm facts to kill theories backfires. The most robust universal theories in science are logically undisprovable by a finite set of observations, precisely because they're so strong and universal.
The unintended consequence is that dogmatic falsificationism condemns the best science we have as metaphysical, because it can't be conclusively disproved. It's scientifically sterile.
So we've established that logic alone can't give us a hard empirical basis. All theories are fallible, all facts are shaky. If definitive disproof is logically impossible, how do we avoid falling into total skepticism?
We have to move from a passive theory of knowledge to an activist one. Since we can't eliminate a theory based purely on a logical refutation, we have to create a conventional, agreed-upon methodology for elimination.
And this is where methodological falsificationism comes in. If we can't find certainty in nature, we create it in our rules of procedure.
Precisely. It's a revolutionary form of conventionalism. We make conventions about singular factual statements. We agree on their truth value, even while knowing that, theoretically, they are fallible.
I love Lakatos's analogy for this.
The pile's driven into a swamp.
Yes. They aren't built on bedrock. We just agree provisionally that the piles will hold long enough for us to build the next part of the bridge.
And this requires the use of background knowledge. We have to decide which theories are under test and which ones we're going to tentatively accept as unproblematic.
So if I'm measuring a new gravitational anomaly, I'm just going to trust the highly corroborated theories of radio optics and data processing uncritically.
You apply them as extensions of your senses. You widen the range of what you call observational.
And this means that methodological falsification is not the same thing as logical disproof.
Not at all. We reject the dogmatic idea that once a theory is falsified, it must be eliminated. Methodological falsification is simply a pragmatic, rational decision to eliminate a theory, even though that theory may still be true.
We eliminate theories not because they're proven false, but because we have better ones.
Exactly. We embrace fallibilism, but we insist on a standard for progress.
This is the crucial pivot. Sophisticated falsificationism stops appraising isolated theories and shifts the evaluation to a series of theories.
We stop asking, is this theory refuted by this data? And we start asking, has this series of theoretical moves improved upon its predecessor?
And the standard for improvement is rigorously defined. The central requirement is that a new theory, T, must have corroborated excess empirical content over its predecessor, T prime.
Okay, corroborated excess empirical content. Let's simplify that.
It means the new theory has to be more than just a patched-up version of the old one.
Much more. It means T must predict novel facts, facts that were highly improbable or even logically forbidden by the older theory.
That prediction of a truly new, surprising fact is the theoretical sign of progress.
And the corroboration of that predicted fact is the empirical sign.
So what we're looking for is a progressive problem shift, and this shift has to be both.
1, theoretically progressive. It has to predict novel facts. And 2, empirically progressive. Some of that predicted excess content must actually be corroborated by observation.
Progress is defined by the degree to which a series of theories leads us to discover surprising, novel facts.
This changes everything. It means scientific growth isn't measured by caution, it's measured by its imaginative reach and predictive power.
And this leads to the most radical conclusion of all.
Which is that a theory is only falsified when it is superseded by a rival theory with higher corroborated content. There is no falsification before the emergence of a better theory.
That is a huge shift in intellectual honesty. You're not allowed to just trash the old idea because you found an anomaly.
You have to hold on to it until you have a demonstrably superior replacement. You must come to the table with an alternative that actually grows our knowledge.
The old criterion was agreement with observed facts. The new one is that the series must produce new facts.
I feel like this is a good moment for a short pause. We've just navigated some heavy philosophical terrain.
I agree. Don't forget to subscribe and leave a like if you enjoy this podcast.
Okay, so if we've moved the standard from the isolated theory to the entire series, we need to know how that series is constructed. How do scientists make sure they are generating a continuous, progressive stream of ideas?
That continuous, highly structured series of theories is what Lakatos called the scientific research program.
It's a structure defined by methodological rules. Rules that tell scientists where they must not change things and how they should change things. These are the heuristics.
Okay, let's look at the foundational piece first. The hard core. What is it?
The hard core is the set of fundamental defining propositions of the program. These are the axioms, the hypotheses that give the program its identity.
For Newton, it was the 3 laws of motion and the law of universal gravitation.
For Darwin, it's natural selection acting on random variation. And this core is protected by the negative heuristic.
The rule that forbids you from directing refutation at the hard core.
Exactly. The core is declared irrefutable by the conventional methodological decision of its adherents. When anomalies arise, the blame must always be diverted away from this core.
But wait, isn't this just a sophisticated way of saying scientists are stubbornly ignoring facts to save their favorite theory? How is this rational rather than just dogmatic?
It's rational because the dogma is only methodological, not logical. We know the core is fallible, but we agree not to test it yet because it's the engine of progress.
If scientists had to reject their deepest theory every time an observation contradicted it,
no theory would ever develop to its full potential. The tenacity is only rational if the program is generating new knowledge.
you protect the core so the program can focus its energy on building the outer structure.
And that outer structure is the protective belt.
The collection of all the movable parts. The auxiliary hypotheses, the initial conditions.
And the ceteris paribus clauses. This belt constantly absorbs the shocks of empirical tests and is subject to continuous adjustment or even replacement. You sacrifice the belt to save the core.
But that sacrifice has to lead to growth.
It must.
So the negative heuristic tells us what not to do. What tells us what to do?
That is the positive heuristic. This is the critical creative element. It's the set of rough guidelines and suggestions that tell the scientists how to change and develop the protective belt.
It drives the continuous, content-increasing development.
And what's crucial here is that scientists in a powerful program are driven by this internal strategy, not just by external anomalies. They're often so confident in their blueprint that they can, as Lakatos said, lie down on their couch, shut their eyes, and forget about the data while they work out the next step.
The program dictates the research agenda. It runs ahead of the data.
It makes the process much more autonomous and directed. It's not constant firefighting. It's a creative engineering project guided by an internal roadmap.
Let's use a real historical case to show the power of this system. Prout's program in 19th century chemistry. The hardcore was
The proposition that all atomic weights are whole number multiples of the weight of hydrogen. An elegant, unifying idea.
But the facts immediately contradicted it. Chlorine's atomic weight kept coming up as 35.5.
And the adherents of Prout's idea did not reject the core. Their positive heuristic suggested that the anomalies must arise from unreliable experimental techniques.
So they decided the facts were wrong, not the theory.
It sounds like cheating, but this is where the progress comes from. The positive heuristic drove them to action. It dictated a massive research agenda focusing on analytical chemistry, designing ever more sophisticated experiments to purify chemical substances.
So it drove a revolution in methodology.
A huge one. And it resulted in a progressive problem shift by consistently improving measurements and correcting the old facts.
So the progress wasn't in defending the core, but in the ability of the core, via the positive heuristic, to generate novel techniques and produce a content-increasing theory of analytical chemistry.
Exactly. The program was only superseded decades later when a genuinely superior idea came along, the concept of isotopes. Until then, Prout's program provided a rational, progressive path despite constant anomalies.
Let's look at Bohr's program in quantum physics because that's often held up as an example of these brilliant but seemingly irrational leaps.
Bohr's program is a spectacular proof of Lakatos' structure. The hard core was defined by two assumptions about electron orbits and energy levels that were blatantly inconsistent with the best physics of the day, the Maxwell-Lorentz theory.
A naive falsificationist would have rejected it immediately.
And many did. But Bohr's program proved rational because it was spectacularly progressive. His first model, M1, aimed to predict the hydrogen spectrum. When his theory clashed with observations, specifically the Pickering-Fowler series, Bohr was not deterred.
So what did he do instead of rejecting M1?
He elaborated the next model, M2. He calculated the expected spectrum for ionized helium and proposed that the Pickering-Fowler series must actually be caused by that, not hydrogen.
He essentially told the experimenters they had misidentified their sample.
A high-stakes gamble. But then, M2 predicted a whole new ultraviolet series for helium, which was subsequently found, providing sensational corroboration.
But the story doesn't end there.
No. The original experimenter, Fowler, found that his wavelengths differed slightly from Bohr's prediction for M2, a genuine refutation.
So M2 is out. Right.
Wrong. Bohr simply introduced M3. He realized that in M2, he'd used a fixed nucleus. M3 corrected the model by considering the electron orbiting the common center of gravity using what's called reduced mass.
And when he recalculated,
They matched Fowler's highly precise measurements exactly. The refutation of M2 became a stunning retroactive victory for M3. The program was transforming defeats into triumphs because of the power of its positive heuristic.
this model of competing research programs completely dissolves the notion of the instant decisive experiment. If every theory is part of a series, how can one single experiment ever be called crucial?
It can't, not in the moment. Lakatos showed that an experiment only becomes crucial retrospectively.
Decades later.
Decades later, after the victorious program has developed, produced a content-increasing version that absorbs the anomaly, and seen that new content corroborated.
Let's take the most famous example. The Michelson-Morley experiment of 1887. It aimed to measure the Earth's velocity relative to the luminiferous ether.
And they found nothing. No movement relative to the ether, a massive negative result.
According to naive falsificationism, that should have killed the ether program instantly.
But it didn't. Physicists operating within that framework were not deterred. They explained it away. Lorentz proposed the length contraction hypothesis.
He suggested that bodies moving through the ether had their dimensions physically affected, contracting just enough to conceal the expected difference.
It was a rational, content-saving move within the protective belt.
But did it predict any novel facts?
Not at the time, no. It was an ad hoc adjustment. The program, for a while, entered a degenerating problem shift. It was just reacting to anomalies.
And the experiment was only recognized as the greatest negative experiment in the history of science decades later.
Yes, and that retrospective recognition is the key. It happened after Einstein's rival program, special relativity, had developed progressively.
Relativity didn't even need the ether concept.
Not at all. And it anticipated a huge, unified array of new, corroborated facts that the degenerating ether program simply couldn't touch. The verdict on the experiment was delivered by history, not by instant logic.
This methodology gives us a vital demarcation criterion, then, a way to distinguish mature science from immature science or pseudoscience.
Mature science consists of organized research programs with genuine heuristic power. They successfully anticipate novel, corroborated facts.
And immature science.
That's composed of programs that have become degenerating. They might be conceptually unified, but they fail to anticipate novel facts. They just constantly react to anomalies by creating these ad hoc, backward-looking adjustments.
This is where Lakatos famously critiqued fields like Marxism or Freudism.
Yes. Look at Marxism. What novel, surprising, corroborated fact has that program predicted since, say, 1917? When events contradict the core predictions, the theory is saved by content-decreasing adjustments, blaming false consciousness, or vestigial capitalist elements.
Explanations fitted to the facts after the fact.
The continuous failure to predict is the sign of degeneration.
If we connect this back to Kuhn one last time, we see how Lakatos solves the tension. Kuhn was right about the tenacity of science, what he called normal science.
But he was wrong to see this tenacity as fundamentally irrational. Lakatos's framework shows that this tenacity is rational if, and only if, the problem shift is progressive.
The direction of science isn't passive. It's determined primarily by human creative imagination.
The powerful positive heuristic and its ability to generate content-increasing theories. It's not just about reacting to negative facts.
It's a project that starts with an imaginative fantasy and then selectively hunts for new facts to confirm that fantasy. Progress is achieved by content-increasing change, not destructive criticism alone.
To briefly summarize our central statements from this incredibly deep dive, we have 5 core takeaways for you.
Takeaway 1. Science is fallible. We have to abandon the dream of certainty. No part of scientific knowledge, neither grand theories nor simple observations, is certain or provable.
Takeaway 2. Rationality is growth. Science is rational, not because it proves true theories, but because it follows a systematic strategy, the methodology of research programs, that ensures continuous, objective growth.
Takeaway 3. The program structure. Theories are organized as a methodological structure built around a protected hard core governed by the negative heuristic and developed through a flexible protective belt, which is driven by the positive heuristic.
Takeaway 4. The progress test. Progress is exclusively measured by the ability of a new version in the series to predict and corroborate novel facts. If a program fails to do that, it's degenerating.
And takeaway 5. Historical judgment. Crucial experiments are never instantaneous killers. They are only recognized as such retrospectively by the long-term superior success of the victorious progressive program that comes later. So if the greatest scientific theories we hold today are merely the temporary peaks of currently progressive research programs, always vulnerable to an imaginative new idea, ask yourself, what fundamental hardcore assumption drives research in your own field today, whether that's economics, particle physics, or artificial intelligence, that you and your colleagues are confident will never be overthrown? And what novel, absolutely forbidden fact might overturn it? Because the logical form of a theory and its presumed certainty depends entirely on the current fallible state of our knowledge, just waiting for the next imaginative leap to supersede it.